The Science of Recovery, Post-Hurricane Succession in the Point Pleasant Park Forest. On September 29, 2003, Hurricane Juan struck Halifax, resulting in immense damages to homes and businesses and uprooting 70% of the trees in Point Pleasant Park. The park, which was planted, resulting in an even-aged evergreen forest, had to be closed for 9 months while it was cleaned up and species diversity was returned. Point Pleasant Park, also known as Amtukati by the Mi'kmaq Nation, was an important gathering place for the Mi'kmaq people, providing them with a space to hunt, fish, and conduct spiritual ceremonies. Our experiment aimed to explore secondary succession in the park over time using species richness, diversity, and evenness in the 20 years since the hurricane by examining the same 6 sites in the park every year. Secondary succession refers to the process where an ecological community renews itself after an event, with nutrients and life remaining in the soil. We hypothesize that if the park does not experience another devastating event, then it will return to its original community composition with assisted regeneration.
Point Pleasant Park is located on the southern tip of the Halifax Peninsula. Following the hurricane, the park was surveyed to determine the locations of 6 study sites whose forest structure was most heavily impacted by the hurricane. Data collection began at these sites post-hurricane in 2004 and continued every year until current day in 2025. This excludes the years 2005, 2007, 2016, and 2020. Only years with complete data collection were included in regression analyses. This study uses a repeated measures observational design with no experimental manipulation. In each study site, all living trees equal to or greater than 2.5 centimeters in diameter were measured in centimeters at diameter at breast height, for which the industry standard is 4.5 feet above ground level. And the trees were identified to determine the density per species per site. For our method of data collection, we used a diameter tape and a guide of common tree species in Nova Scotia or plant identification apps like iNaturalist to identify the species. Additionally, percent ground flora cover was sampled using randomly placed 1 meter squared quadrats within each site, excluding trees within the quadrat. Each site is a replicate, and data was later pooled to conduct statistical analyses on the park's status as a whole. Regression analysis was chosen as the statistical analysis because it allows us to test the rate of change in a variety of community metrics over time. It works very well for studies with replicated sites because it can estimate overall trends while accounting for variation among sites. Raw tree data was calculated to obtain total density, richness, diversity, maximum diversity, and evenness. These values were then used to perform regression analyses using RStudio. We used regression analyses of total density, comparison of red maple density to red spruce density, and Palouse evenness to examine changes in the forest community of the park since 2004.
To examine the overall forest community, we measured the number of individuals of each species at each site every year from 2004 to 2005, as shown in Figure 1. The total density of species increased 23 times the amount from 2004 to 2025, with 2004 having an average of 5 and 2025 having an average of 117.2. We can predict that the overall community will reach its maximum species richness and density as the forest moves towards its climax community because there will be younger trees to help buffer winds and support community growth of the forest.
From these two graphs, it can be seen that the density of red maple has increased at a rate of 2.24 individuals per year, which is approximately 6.5 times faster than the increase observed for red spruce over the same 21-year period. Comparingly, the density of red spruce increased at a rate of 0.35 individuals per year, which is much slower than the red maple's rate of increase, indicating that red spruce is less rapidly expanding in the forests of Point Pleasant Park. These patterns are reflected in both their trend lines, which show positive relationships between year and density. As the forest approaches its climax community, red spruce is expected to gradually become the dominant species, while red maple will likely decline in dominance over time. This is because red spruce is shade tolerant and a late successional species, and multiple studies, such as Jocham and colleagues in 1985 and Turchin in 2016, both identify red spruce as characteristic of mature and overmature forests in this region. In contrast, red maple is shade intolerant and tends to dominate early to mid-successional stages, especially after disturbances such as hurricanes, which is supported by the study done by Burley and colleagues in 2008, who found that red maple was abundant in canopy and sapling layers following storm-driven regeneration. As the light availability decreases, conditions will increasingly favor shade-tolerant species, like red spruce over red maple. This may likely lead to red maple declining in relative abundance over time, which will lead to a shift towards a red spruce-dominated community.
Looking at this figure, there is not a significantly distinguished trend in the line of best fit. While it shows a slightly decreasing slope as supported by the negative yet small m value in the equation of the line, there are no significant regression results. This indicates that there is insufficient statistical support for the correlation of the data with the best fit line. These results indicate that there was no significant change in total evenness between 2004 and 2025 in the observed sites, which does not align with successional theory and similar observations occurring within the post-hurricane growth in the park. There does exist large differences between sites, which likely contributed to the lack of significance in a larger trend of evenness over the years. This data instead supports the possibility of microhabitats within the differing sites, which could have been caused by differences in environmental factors as well as human activity, like habitat fragmentation and management. As the forest moves to its climax community, the evenness metric is expected to stabilize. Over time, possibly the differences between sites will decrease as the forest matures and stabilizes. In examining the secondary succession of the Point Pleasant forest since 2003 Hurricane Juan, the results of this study predict this urban forest to be at a mid-successional stage. The total tree density is increasing at an accelerated rate over time and has not yet plateaued. The fast-growing shade-intolerant red maple is spreading at a faster pace than the red spruce, a species associated with late succession and shade-resistant slow growth. This restoration has displayed how forest health in an urban context can be affected by numerous factors. This includes the fragmentation of forest habitat by walking trails for park visitors, and also the active management, mostly removal, of important ecosystem characteristics like logs and dead trees for the purposes of public safety. These factors also impact the natural restoration of such urban sites. This could be causing the microhabitat effect unevenness between sites as discussed. In looking at this data and examining pre-existing management strategies, a more informed forest health forward plan can be developed to balance this into recreational priorities. In moving forward, the concept of Etowuptimuk, or two-eyed seeing, is a modern-day Mi'kmaq teaching which emphasizes the benefit of multiple distinct perspectives. In using one eye of traditional Mi'kmaq knowledge paired with another of Western knowledge, a balanced path towards improving a reality can be achieved. In applying this to Point Pleasant Park, using traditional Mi'kmaq forest management knowledge and that of local species paired with Western research and methods, this urban park can be assisted in growing into and remaining a healthy Acadian forest for all to appreciate. This requires the significant involvement of Mi'kmaq knowledge keepers and specialists in management, a change which needs to occur now for the health of all peoples and ecosystems.
First and foremost, the land upon which we collected data, Amtukati, or spiritual place, was lived on and used by the Mi'kmaq Nation for thousands of years before us. We would like to thank Dr. Allison Schmidt for her contributions to past data collection, data analysis, and graphs. We are also grateful to Dr. Joanna Zagoras for coordinating data collection, performing our data analysis, and creating the graphs used in this presentation. A big thank you to all the TAs and students of present and past who participated in the data collection in Point Pleasant Park. We would also like to preemptively thank our peer reviewers for their constructive feedback on our presentation. Finally, thanks to Dalhousie for providing the materials needed to collect the data.
These are the references used throughout the presentation. Thank you for listening.